Now, in the previous videos, we were talking about the basics of ANOVA and how we can use this approach to make comparisons across more than two sample means. But what I want to do in this video is to really get into some of the nuts and bolts of ANOVA. How is it that ANOVA calculates these things like mean squares and F statistics that we might use to test our null hypothesis that all of the sample means are equal? If you recall, the basic idea of an ANOVA is to determine what the ratio is of variation among groups relative to variation within groups. And so we've been talking about this example where researchers exposed ground squirrels to cold, hot, or warm ambient temperatures and measured their body temperatures. And so here you can see in this graph that ground squirrels experiencing cold temperatures had lower body temperatures than those experiencing warm or hot temperatures. So how can we test whether these means are different from one another using an ANOVA? Well, here is what the data look like, where we have 20 observations under cold temperatures, 21 observations under warm temperatures, and 20 observations under hot temperatures. And we can summarize these data using some measurements that you're already familiar with. We have our sample sizes for each of these three samples, our sample means, and our sample standard deviations. Here we have three samples that we're comparing, and so K is equal to 3, where K is the number of samples or the number of groups in our study. If you recall, in our two-sample t-test, we're testing the null hypothesis that these population means are equal to one another, and we test this using a t-test statistic where the difference between sample means is included in the numerator and the standard error of the means is included in the denominator. In the case of an ANOVA, where we're comparing more than two sample means, we perform what's called an F-test, where we're testing the null hypothesis that all of the sample means are equal to one another, regardless of how many samples we have. And we use an F-test statistic to determine whether or not these means are different from one another. Now, an F-test statistic is calculated as the ratio of the mean square between over the mean square within. And we used this F statistic in the previous video to compare against an F distribution to calculate a p-value. But what I want to do in this video is to go into a little bit more detail about how we calculate these mean squares and what they mean. The basic idea of these is very similar to our two-sample t-test, where in the numerator, we have some measurement of the difference between means, in this case, between the two sample means, in this case, among all of the sample means, relative to the amount of noise or how much uncertainty we have within each of those samples. So what does this mean square between actually mean? Well, in this notation, MS stands for mean square, and the mean square between is simply a measure of how different the group means are. That is, how much variation is there among groups. The way we calculate a mean square between is roughly as the squared deviation between the mean of each group and the grand mean. And what I mean by the grand mean is the overall mean across all of the samples. And so here we have the grand mean of all of our 61 samples of ground squirrel body temperatures, where that grand mean is equal to 36.39 degrees Celsius. So the mean square between then is a measurement of how different each of these sample means are from the grand mean. So the cold sample mean was much less than the grand mean. The hot sample mean was much higher than the grand mean. And so the mean square between is simply a measurement of how different each of these sample means are from the grand mean. And if you remember, I mentioned that we calculate this roughly as the average squared deviation of each sample mean from the grand mean. Squared deviations, just like our variance calculation, because we don't necessarily care about the direction, just the average magnitude. On average, how different are these sample means from the grand mean? And we can do this using this equation here, where we are calculating the squared deviations of each sample mean, going from the first one to the last one. So how different is the sample mean from the grand mean? Square that so that we only consider the magnitude. And this is what I'm talking about when I'm talking about the squared deviation. Okay, very similar to our calculation for our sample variance, where we're taking the sum of squared deviations of each observation from the sample mean. Okay, in this case, we're saying what is the average squared deviation of each group mean from the grand mean. And so we're summing up all of these deviations, starting with the first group and going to the last group. In our ground squirrel example, we had 3 groups or 3 samples, so K was equal to 3. Now I mentioned this is not quite like an average squared deviation because we've got this term in here for n sub I. This is the sample size of sample I. And so it's not entirely an average squared deviation because we've got this sample size mixed in here. And all that's doing is just to create the equivalent of like a weighted average. So samples that have a larger sample size are going to weight more heavily into our calculation of our mean square between than samples that have a smaller sample size. Okay. Now, remember that in our denominator, we're using K minus 1 rather than K because we're dealing with deviations that must always sum to 0. So the sum of all of our deviations across our samples from the grand mean are going to sum to 0. And so as a result, we divide by K minus 1 rather than K. But in essence, what you want to think about when you look at this is roughly the average squared deviation of the group means from the overall grand mean. Now, when we're talking about our mean square, then we can define the numerator and the denominator more explicitly. What we're talking about when we're talking about this numerator are what's referred to as the sum of squares between. So the sum of squares between groups. So this refers to the sum of squared deviations of each group mean from the overall grand mean summed across all 3 of our samples. Okay, so the sum of squared deviations of each sample mean from the grand mean. And in the denominator then, what we have is our degrees of freedom between groups. Okay, which is calculated as K minus 1. So this is the signal part of our F statistic, but what about the noise part? Well, the noise part of our calculation is referred to as the mean square within, which is simply a measure of how much variability there is within each of our groups. And it can loosely be thought of as a weighted average of the variances of each sample. Okay. So here we have the variance of sample I, and we're just weighting it again by the sample size of sample I. So samples that have a larger sample size are going to weight more heavily into our mean square within calculation, but you can loosely think of it as roughly a weighted average of sample variances. And just like the mean square between, the mean square within has a numerator that we refer to as the sum of squares within, okay, the sum of squared differences between each observation and the sample mean, divided by our degrees of freedom within. So here we have an F statistic then that's calculated very similarly to our t-test statistic, where in the numerator we have some measurement of the magnitude of the differences among groups, and in the denominator we have a measurement of the differences within groups. So what we're really measuring then is how big are these differences among sample means relative to the variability that we have within each of these sample means. The higher the signal to noise ratio, the larger the F value. So the bigger the differences among means, the larger the F. The smaller the variation within samples, the larger the F. Now we can depict all of these different components of our F test statistic in what's called an ANOVA table, where we report the between group effect and the within group effect as separate rows in our table. And we have degrees of freedom, sums of squares, and mean squares. If you recall, the mean square is just the sums of squares divided by the degrees of freedom. So our degrees of freedom for our between group effect is equal to the number of groups minus 1. So in our ground squirrel example, that was 3 minus 1 equals 2. Our degrees of freedom for our within group effect is the total sample size minus the number of groups. And our total degrees of freedom then is the total sample size minus 1. We can calculate these sums of squares then as the sum of squared deviations of each group mean from the grand mean in our between group effect. In our within group effect, the sums of squares are roughly the variances within each of the groups. And our total sums of squares then is the sum of all of the squared deviations of each observation from the grand mean, summed across all observations within each group and summed across all groups. So we can take these sums of squares, divide them by the degrees of freedom to calculate our mean square. And we can do this for the between group effect as well as the within group effect. Now, what's really neat about this ANOVA table is it makes clear that these sums of squares and degrees of freedom add up to total sums of squares and our total degrees of freedom. So the total sums of squares is equal to the sum of squares between plus the sums of squares within. And our total degrees of freedom is equal to the degrees of freedom between groups and the degrees of freedom within groups. So what we're doing in an ANOVA then is to simply say that we can decompose all of these differences between each individual observation and the grand mean. And we can explain or describe or decompose that difference into two different parts. The difference between the group mean and the grand mean, and the difference between the individual observation and its group mean. We can say that this deviation from the overall mean is equal to the sum of the deviation of the group mean from the overall mean and the deviation of each individual observation from its own group mean. In terms of pictures then, we're saying that the deviation or the difference between each observation and the grand mean can be described or decomposed or broken down into differences among groups plus the deviations within groups, meaning the deviation of each observation from its group mean. And that's what I mean by the fact that these total sums of squares is equal to the sums of squares between groups plus the sums of squares within groups. Okay, so let's walk through our ANOVA table then for our ground squirrel example. If you recall, we had 3 samples in this example, squirrels that experienced hot, cold, and warm temperatures. So in this case, the number of groups or number of samples is represented by K, And so our degrees of freedom for our between group effect is k minus 1, which is equal to 2. Now, if you recall, there were a total of 61 observations in this experiment. So our total degrees of freedom is equal to 60. And our within group degrees of freedom then is our total sample size minus our number of samples, which is 61 minus 3, and that equals 58. Now, if you recall, we can check our math because we know that the between group degrees of freedom plus the within group degrees of freedom needs to equal the total degrees of freedom. Okay. Now, if we were to take these data that I showed you earlier on and calculate our sums of squares, we could calculate the between group sums of squares as 1021.7, the within group sums of squares as 15.5, and the total sums of squares of 1037.2. Now, just like the degrees of freedom, the sums of squares are also additive. So the between group sums of squares plus the within group sums of squares needs to total up and equal the total sums of squares. Now, from these sums of squares then and degrees of freedom, we can calculate our mean squares. So our mean square between is simply our sum of square between divided by our degrees of freedom between, which is equal in this case to 510.8. The within group mean square then is equal to the within group sums of squares divided by the within group degrees of freedom, and that's equal to 0.3. We can use these mean squares then to calculate our F statistic, which is simply the ratio of the mean square between divided by the mean square within, which in this case is equal to 1,906. And with this F statistic comes both a numerator and a denominator degrees of freedom. The numerator degrees of freedom is the between group degrees of freedom, and the denominator degrees of freedom is the within group degrees of freedom. We can then take this F statistic that we've calculated and compare it to an F distribution with 2 numerator degrees of freedom and 58 denominator degrees of freedom to determine how unusual this calculated F statistic really is. And we can see that with 2 numerator degrees of freedom and 58 denominator degrees of freedom, that most of the time when the null hypothesis is true, we're going to get an F test statistic in and around 0 or 1 or maybe 2. And only very rarely are we going to get F statistics in the 4, 5, or 6 range. And in fact, we can calculate that the critical value corresponding to a p-value of 0.05 for an F distribution with 2 numerator degrees of freedom and 58 denominator degrees of freedom is equal to 3.16. And our F value is way beyond that, way off the charts over here. And so the p-value that we'll calculate for this F statistic is actually going to be very, very small. And we can do this using R, where we get our ANOVA table reported out for our summary of this AOV, or analysis of variance command. And just to orient you to the way this is depicted, the between group effects are shown here in the top row, and the within group effect is shown in the bottom row, referred to as residuals. So we have our numerator degrees of freedom, our denominator degrees of freedom, our between group mean squares, our within group mean squares, our F value, which is simply this divided by this, and our P value, which is in fact very small. And in this case, because we have a very small P value, we reject the null hypothesis that the means are all equal, and instead have compelling evidence that the body temperatures of ground squirrels differs among these 3 experimental treatments. So in summary then, an ANOVA uses an F statistic to calculate a p-value. An F statistic has both a numerator and a denominator degrees of freedom. F measures the ratio of differences among groups relative to differences within groups. The bigger the differences among groups, the bigger the F and the smaller the P.